So, good evening to all the attendees. Welcome to week 8 of Electrical Machines NPTEL course. I am Sai Krishna. So, this week we will be continuing with the second session of DC machines. So, last week we discussed the introduction in DC machines, the construction, the armature winding, the winding patterns, and the how the winding is being wound, and also some more concepts on DC machines we have discussed. So this week we will be seeing a more important concept, that is how the EMF is being generated in a DC machine, and how do we calculate the EMF generated in a DC machine. And along with EMF generation, we will also discuss how we can calculate the force acting, like the force equations, and also electromagnetic torque generation, and how we can calculate the torque. So these three concepts we will see today, and based on that we will solve a few numerical questions which will be helpful for your assignment. So let's start today's discussion. So 1 second. Yeah. So suppose let's say we have a DC machine with field winding and armature winding. So we know in a DC machine we will have typically a field winding and also the armature winding. Let's say you take a DC machine and you will run the machine with the prime mover, and at a certain speed. We will call often in electrical machines the speed in terms of rotations per second or rotations per minute, RPS or RPM. If it is RPS, we will if it is in seconds, we will say RPS. If it is in minutes, we will divide RPS by 60. So that's conversion is fine. Now I know field current, which will create the flux along the machine. Let's say I will just draw this machine now. I'm just drawing the DC machine. These are the armature terminals where I will take the voltage output. Let's say this is A1, A2, and here I have my field winding, right? So yeah, field winding is F1 and F2. Let's say I pass a known current of IF through the field winding. So yeah, now when I pass a field current, now the machine is already under the influence of poles. Now the current which I have passed will create flux. Like, see, now the flux will be generated per pole. Let's say this phi is flux per pole, and there is current passing through it, and now the EMF will be induced. Now I would like to know the EMF available across the brushes of the machine. So across these A1, A2 terminals. Now I want to know what is the available amount of terminal voltage. So, and apart from that, I will also want to know on what factors does this armature voltage depends upon, and how we can calculate this armature voltage of the terminal center. So that we will see today. Now consider a DC machine. Now here I have mentioned a flux phi is a flux per pole, and if you pass a known current of IF, the poles N and S will be created inside the machine, and as flux is generated, we have a flux per pole is created, and now I decide to run the machine in a particular direction. So with a speed in RPS, that's what I was saying, RPS or RPM. Now across A1, A2, I want to calculate how much voltage has been generated. Now before going to that, if it is generated, I want to rotate my machine. So I will rotate my machine using a prime mover. Prime mover is nothing but a shaft type of will be there, and I will rotate my machine physically, like mechanically with a prime mover, and then it starts rotating, then the EMF will be induced. So now by a prime mover, I have driven my machine, and now the question is, what is the generated voltage? Let's say I have connected a voltmeter here. Now how much this voltmeter will read? How much is the voltage that my voltmeter will read? That's the question, because I have not connected any load here. The no load terminal voltage across my DC machine terminals I want to know. Now before proceeding to that voltage calculation, now just let's start from the basic. Now how to calculate the flux initially? We know when we pass a known current of IF through the field terminals, a flux is generated. Now let's first calculate the flux per pole, and then we will see how we can get the voltage from it. Now, yeah. So let's say how to calculate flux per pole calculation. Flux calculation is pretty simple. We all know the formulas. Like if you know the current and you know the number of field winding turns, you will get the MMF, right? So yeah, flux is equals to MMF by, so R is nothing but reluctance. Reluctance will be there for that material, and you know the MMF, you will easily get the flux. I will specify this is flux per pole. Now, if flux per pole is known, now the EMF is required. Now I want to calculate the EMF equation. Now, before going into EMF, last week we discussed now my flux density distribution across the DC machine. We have seen the trapezoidal waveforms of flux distribution last week. Now I know the nature of my EMF induced will be same as my same as my flux density distribution. That also we have seen last week. Now let's calculate the flux distribution first, and then we will arrive at the EMF voltage equation. Now we know the distribution of flux in a DC machine is trapezoidal. The reason also I think you remember why it is trapezoidal. It is because the poles. I just quickly draw here. If it is a rotor now, so here it is air gap. This is the second pole. So in this is a mid 45-degree angle between these two. Here there is no this air gap is maximum, so there won't be any flux distribution here. Now as we reach here, the air gap is minimum, and we have a constant flux distribution here. So that's how the flux is being generated. That is a trapezoidal flux. So I'm just brushing up the topic again. So yeah, so this is my B, that is flux density, and this is my space angle, and my conductors are placed in this fashion. And yeah, let's say this is 0, and this is pi, and this is 2 pi. Now the nature of B will be the nature of EMF and value of B. But if you see the nature, I know it is a trapezoidal nature, but if you see the value of B distribution, it is continuously varying with space in time. Now at 0 there is no flux, but at some, let's say 30 degrees and 60 degrees, 90 degrees, like 150 degrees, 120 and 180. From if you see 0 to 180, my value of B is continuously varying. It is varying with time. And let's say my armature conductors are moving. These all conductors I have drawn here. These are the armature conductors, and of course my field is stationary. My field winding will be stationary. It won't move. It's a separately excited. So my field winding is bound on the poles, right? North and south poles. I just draw it here. So let's say this is north, south, north pole. My field winding will be wound like this. This won't rotate with the machine. So the windings on this armature this will rotate. Rotor. Now my field is stationary. Say I have created south pole, and let's say this is north pole. Now we have to apply. There are some Now there are right hand rules and left hand rules in our electrical machines. It's applicable for entire electrical engineering. These are the basic rules which we will apply to know the directions of dependent parameters. Now let's see here we have, okay, now let's say we need to find out the voltage induced in each conductor direction. Now let's take this particular conductor. Let's say I took this conductor, and I want to know what is the direction of armature voltage. So now see, induced EMF voltage direction I want to know. Now for this particular conductor, my field is in top direction. Now my field is in this direction, and my conductors are moving with respect to time. If you see, as my rotor rotates, my conductors will move along south. At this point, the conductor is in south position, and after some time, it move along with the space angle, and it will come into north under the influence of north. Now, if you see, the velocity is in this direction. Now I know what is the direction of field and what is the direction of velocity, and with right hand thumb rule, we will know it's not right hand thumb rule; it's a right hand rule. With using that right hand rule, we will know the direction of induced armature voltage. Now let's say how we can know that. It's a right hand. Everybody, take your right hand and you keep it like that. And uh, 1 second. See, this is uh,
Sir,
yes.
hello.
Hello.
Sir, please confirm me that for motor we apply left hand rule, no?
It's common for motor or generator. It's a DC machine.
O- Okay, sir.
If like it's see the generation and the consumption of if if the motor is generating voltage, that is generator. Now if you generate if you are generating some voltage and you are giving that voltage back to a machine, like if my machine is acting as a load, then it's a motor. Now if you are driving your motor with a prime mover, means it's a generator. This law is applicable for all kinds of machines. Now it's not like we define it for motor, it's defined for generator, but the principles apply in that condition, because we are here when we talk about generator, we will talk about field first, velocity first, and voltage later. That's why we use right hand rule. When it comes to motor, we are already giving supply directly to it. So that's why we don't talk about right hand rule. In the left hand rule, we will talk about direction of force. We will come to that point later. In that, when we come to the torque derivation, we will see we will use left hand rule, because left hand rule will give us the direction of force, the thrust, the direction of movement of the machine, that we will see. So basically, you don't. I will not suggest you to remember like motor left hand rule, generator right hand rule, but just remember the rules, and whatever component you want to know the direction, you apply it, and that's my suggestion. Okay,
Okay, sir, I am taking individual.
yeah, if you remember it individually, it's like you are remembering things that will at some point you might forget also. Now you go with the basics, and if you see, if you want to know the voltage induced direction, that will be useful for generator, because you will be applying the field first, then voltage is the cause of it. Like voltage is the effect of it. Here the cause is field. So in that way, you will know you have to use right hand rule for the generator. So that's how you should remember it. Okay.
Okay, sir, clear.
Okay. So here see, let's say you can take your right hand, and if my thumb shows the direction of the velocity. It means the direction of motion. Any body you take, the thumb represents the direction of motion. Here the motion is associated with the conductor, right? And but in a particular conductor, we are trying to find the direction of voltage. Now take that conductor. I know my velocity is going from left to right, right? Okay, left to right. So my thumb is from left to right. Fine. And my index finger will be the direction of magnetic field. Now if you see from the direction, the field is in this direction, bottom to top. Now my thumb is in the direction of velocity, and my index finger is field, right? I'm just taking it up. Now this is the direction of velocity of my conductor, and this is the direction of field, and my middle finger, that will show us the direction of induced EMF. That's the right hand rule you need to remember. Now I know I'm just keeping it in the figure, and this is the direction of velocity, this is the direction of field. The perpendicular direction will be induced EMF. I will just mark it here. So if I take conductor here, and this is the voltage, and this is the field, and this is the voltage of induced EMF. Now the EMF polarity is coming out of the paper, right? Coming out of the screen. So that we denote it by dot. If it is going into the plane, we know it is a cross convention. Now, yeah, you remember it. This is the thumb, and this is the top finger, okay, and this is the middle finger. Okay, whatever. Just yeah. So this is how my hand is. So this is my middle finger, this is my index finger, and this is my thumb. So yeah, so that is the direction. Now we know that all the conductors under the south pole will have my induced voltage polarity coming out of the paper. Now all these conductors will be denoted by the dot convention. Now same thing, if you see for north, obviously it will be cross convention, but let's just verify it whether we are getting uh, cross convention or not. If you see that the field is in the downward direction and voltage is still from left to right, and now see velocity is in this direction and my field is in this direction. Sorry, okay, field in this direction. Yeah, in this direction, field is in this direction. Now my middle finger will show the direction of induced EMF, that is into the plane. So I will denote it by cross. It's all based on conventions. Okay, so all conductors are now placed under south pole, either south pole or either north pole. Now however, the magnitude of voltage, if you see, now we have just arrived at the only polarity of this polarity of the induced EMF, but not at the magnitude. Now if you see the magnitude, it will depend on the magnitude of field index, the B. So if you take again, there is a small if you see at this point, let's say at this point, if you are taking B, it is this value only. Let's say it's B1 at point A, and if you take it point B, it's again B, na? Let's say it's a point C. At point C, it is B2. At point A and point C, we have different values of B1 and B2, right? And that value will change if you take one conductor. Uh, it's during its entire motion from 0 to pi, it will experience a variable field from 0 to pi. Now what the electrical engineers were doing in this condition was, from period 0 to pi, they are taking the average value of B, such that we will get average value of B. Even that will also give you the exact answer. Now if you integrate from 0 to pi the value of B with respect to this limits, you will get the average value of B. So that is not wrong. You will also get the exact value of the B average. Now if you see for this kind of trapezoidal field distribution, this dotted line will just represent the B average. Now uh, this will be the B average. Yeah, uh, sorry. Yeah. So let's say polarity, we already know on the south pole what is the polarity, and north pole what is the polarity. So what we can do is we will calculate the B average and we will proceed with the calculations. Now say let's say we have the value of B now. Now we will need the induced voltage in every single conductor. What I will suggest is, if you want to calculate the total EMF generated across the armature terminals, you calculate first for a single conductor. Then we will see, we will multiply with number of conductors, or we will see how much total induced EMF will be generated for all the conductors based on what different parallel paths present in this machine. Now let's say a single conductor. We already taken a single conductor. Now this single conductor is passing from 0 to pi. So induced voltage is not constant in 0 to pi, because each single conductor is experiencing different values of B. Now what we can do is, we will we will see what kind of B it is experiencing, and from 0 to pi we will take the average value of the flux density, and we will proceed with the EMF generated calculation of EMF generation. Now I will just see. Okay. Okay. Yeah. So, but we know that we have to calculate the B average. But how to arrive at the B average? How can we calculate the average value of flux density? That's the question, right? Now, see, I'm just drawing a machine. Okay. Let's consider a 4-pole machine. A DC machine is comparatively very simple compared to the other machines you have. Okay, so let's say it is not. Okay. Let's say we have a 4-pole machine like this, and suppose the diameter of the rotor. I will just write the terminals, whatever. Diameter of the rotor is equals to D, and and let's say it's a 4-pole machine, and yeah, I'm just taking a single conductor in under the influence of any one pole, and we will see how much now we'll see how much is the flux per pole. Now the units will be, diameters will be in meter, and flux per pole will be in Webers. And see, if you take this pole, this is the south pole, and under this pole, the flux will be for this particular pole. This along this length, this part of the machine is under the influence of south pole, right? Now you need to know the length of this particular length of that particular part length you need to calculate. Now how can we find that? Anybody have any idea how to get this particular length? Because it's a circular machine. The shape is circle. Now you know the entire circumference of the circle, and that particular length will be how much? What is the total length of circumference? It's 2 pi r, right? It's in here. If diameter is d, the length will be pi d. It is the total length of the machine, that is a rotor, and you divide it by number of poles. Because it is 4-pole machine, from here to here it will be at the south, from here to here it will be at the north. So there will be four such sections. If you add all the four sections, you will get pi d. Now I am interested in that particular part. It is nothing but pi d by p. Length is equals to pi d by p, which is in meters. Now calculate the area. Okay. Because why are we calculating this? We know the EMF formula will be E is equals to BLV, right? Now I'm trying to calculate PV, and then we know the length, and then we will see the value of velocity. Now if we multiply all three, we will get E. But before going that, we need to calculate the B average. B average is nothing but flux by area, and that's what we are trying to calculate. We know what is flux per pole, and if you can calculate the area, you will get the value of B average. Now you substitute B average in this formula and you will get the EMF generated equation. Now can anyone tell me the area through which this flux is acting? Because area through which flux is acting, because we are interested in only that particular area. Now see, pi d by p multiplied by length. Here L, because area is nothing but that particular length, that particular arc length into total length of the machine. You will get the cross sectional area, and this unit will be meter square. So now can someone tell me what is V average here? Flux per pole divided by area is equals to flux per area. How much it is? Pi d by p into L. So pi p by pi dl. The units of B average will be Tesla, because that's the field, magnetic field intensity, magnetic flux density. So yeah, we now know the B average. Now let's calculate the velocity. Fn, we already said that in starting. If we are trying to rotate our machine with rotations per second, RPS, we will say n. And if n is RPS, sorry, yeah, V is equals to my linear velocity. Yeah, V is to get velocity from rotations per second. How will you do that? Anyone, any idea? Rotations per second is time quantity. Per second, you will know how many rotations your machine is doing. Now to get the velocity from it, it's a meters per second. How will you get it? It's nothing but we have to multiply with the length of the machine, right? Velocity is equals to distance is equals to time into speed. Now, if you need to get speed, you have to multiply the distance divided by time. Here, and RPS is nothing but frequency. At what rotations per second, cycles per second you are getting. So you multiply that RPS with the length of the machine, you will get the velocity. That's simple. So now what is the length of the machine? We already calculated here, pi d. The total machine, because we are calculating total velocity. Now pi d multiplied by L. So this is V. Now we know V average, and we can calculate E. E is equals to, can I keep the charge? E is equals to B average into L into V. So how much is B average we got? 5P by pi dl. 5 is flux per pole, P is number of poles, pi dl multiplied by L into V. How much is V? sorry, pi d into n, right? Pi d is length. Pi d n, because it's the frequency multiplied by length, pi d n. The units will be meters per second. L into pi d n. So the pi d l, pi d will get cancelled, and you will get pi p n. Now, what is the EMF induced we got? Phi p n. What is the unit of it? Volts. Voltage. Let's say induced voltage, right? Now, what we got here is for single conductor. Now, what we are trying to actually calculate the total induced voltage appearing across the armature terminals. Now, let's say if we know how many conductors are there in total, you can just multiply this EMF equation with this Z, the total number of conductors, you will get the induced voltage equation. So that's how you do it. Now, how to get the conductors? Now, that we already know. So let's say this is my slot. Last week we see it. Last week we saw the winding scheme also. This is the lower deck of the slot. This is the upper deck of the slot, and this is one coil slide, and this is one coil side, and each slot is having two coil sides, right? Let's say my total number of coils are S. Now by the number of coil sides will be 2S. One more thing, each coil will have number of turns. Now let's say my each coil is having two turns here. Turns is nothing but this only. This is single turn coil.
Hello,
Yes.
sir. Can you explain it from starting little bit for better clearance?
Which part?
Sir, from starting, sir.
Okay, from EMF generation part.
Yes, sir, from EMF
Okay, okay, fine.
and from.
Fine, I'll do that. Let's just complete this final expression and I will just complete that.
Okay, sir.
So this is a single turn if you see like this, and I have turned it two times. This is a two turn coil, and this is coil side, and this is another coil side. This entire turn will constitute the coil. Now, if you see, to get the number of conductors, I am just saying that you have to multiply this total number of coil sides into the number of turns. That will give you the total conductors. Now, yeah, say Z will be, yeah, let's say my total conductors are Z, and the voltage will be same if, let's say, there are two parallel branches. We know in transformers also we discussed. If it's a parallel branch, the voltage will be same across these two parallel branches. That's in a parallel branch the voltage will be same. Now, if in a DC machine, if you have four different parallel paths, based on this is the four pole machine, four pole lap winding machine. We already discussed the kind of lap winding machine winding pattern in the last week. So if there are four poles, you will have four parallel paths. Now the voltage induced will be, you have to calculate for not all the conductors, but number of conductors in single parallel path. So that's very important, because you can't just multiply this with all the conductors, because the conductors are divided between different parallel paths. So that's what. So let's say Z is equals to number of conductors, Z by A will be conductors per parallel path. We have to multiply this EMF equation with this particular term, because across all the parallel paths the voltage will be same. Now the final EMF equation will be phi happen P n multiplied by Z by A. Now if you once design the machine, now once the machine is designed and all, this number of conductors will be constant, number of parallel paths will be constant, and the number of poles will be constant. Now the only variables will be the flux generated and also the speed at which the machine is rotating. Now nz by a, sorry, pz by a. So this is the EMF generated equation. EMF generated equation where the bracket terms will be always constants because number of poles is constant, number of conductors is constant, and the number of parallel paths will be constant once you decide the machine. The only variable quantities will be flux and which is the speed. Okay. So as one of the students was asking me to discuss this EMF generation again, let's see from where we have started today, and we'll just quickly do the revision. Okay. Uh, let's say we have a DC machine and we have field winding and armature winding, and now I'm giving my field winding current of IF. Now when I pass my field winding with a current IF and which is on the poles of a DC machine, my poles will be created, flux will be generated. Now my rotor, my armature winding is under the poles, and the EMF will be induced because my flux is generated inside the flux winding, field winding, and that will cut the armature conductors, and EMF will be induced in the armature winding. Now the figure you are seeing here is the flux field distribution in a DC machine. The nature of field distribution in the DC machine will be trapezoidal because based on the pole structure and also the air gap, you will get a trapezoidal kind of nature. And in the figure you can see the distribution of conductors. Yeah. So here we can see the conductor distribution under each pole. Now, in order to calculate the EMF equation, you need to first calculate the field distribution, that is B. And next you have to multiply that B with length of the machine and velocity of the machine to get the EMF induced. Right. Now, how can we calculate the B average? So before proceeding to B average calculation, we have to determine what should be the polarity of the EMF. Now, EMF polarity can be decided by the right hand rule, where in the right hand rule, my thumb will denote the velocity of the motion and my index finger will denote the direction of the field. Then my middle finger will give you the direction of the induced EMF. Based on the right hand rule, we have determined the EMF polarity, that is dot convention under south pole and cross convention under the north pole. Now we have arrived at the EMF polarity, but we need to arrive at the magnitude of the EMF. To calculate the magnitude of EMF, we need to calculate the magnitude of B. But B is varying under this field. Now if you see from 0 to pi, we have variable values of B. So how can we get a constant B which will be used in the equations? So the solution for that is you calculate the average value of B from 0 to pi and you proceed with the calculations. That is also a correct method. Now, how to calculate the average value of B? If I know my flux and also the area under which my flux is acting, my field density is nothing but flux divided by area, Weber per meter square. Now I know the flux distribution because I know the IF current, that is a known current I'm trying to flow it in the field current, and if I divide it with the area of that particular area, I will get the flux B, flux density. Now how I calculated the area? Area is nothing but under the section flux per pole. Here how many poles are there? 4 poles. So under each pole there is some amount of flux is being generated, that is we call flux per pole. Now, if this is the pole, only this particular area is coming under that pole, this particular area. Now, only calculate the length of this particular arc, and you calculate the area of that part, and you will get the area. Now, so how much is this length? The total length is 2 pi r, that is pi d. Now this is only the fourth part, that is one fourth part of the pi d. So that's how we arrive at this pi d by p. Now my p will change. If it is only two pole machine, this part will be under this pole and this part will be under this pole. So if it is two pole, pi d by 2. If it is four pole, pi d by 4. So to generalize it, we have make it as pi d by p. Now you multiply that with the length, you will get the area. And you multiply it with L, pi d by p multiplied by L will give you the area. Now,
Sir, P represented a pole or perimeter?
no. P is number of poles. Here I wrote, right?
Poles.
Diameter of the
Okay,
rotor
okay.
is D. Flux per pole is P. I will also write this. P is equals to number of poles.
Okay, okay.
Yeah. So flux divided by area I did to get the value of B average. Now, once I get the B average, my EMF induced will be BLV, where L is length and V is velocity. How to get velocity? Velocity is nothing but by frequency multiplied by length of the machine. Again, length of the machine is pi d. We have just calculated pi d is 2 pi r multiplied by frequency, that is n rotations per second. Now I know B, now I know L, now I know V. How can you calculate the E? That is BLV. So that we calculated here BLV. B is phi p by pi dl multiplied by L multiplied by pi dl. You got the expression for EMF induced phi pn, and this is the only EMF induced per conductor that I will write here. That is only for conductor, per single conductor. Now, if there are total z number of conductors, and those z number of conductors will, if we are having four parallel paths, z by 4 will be that amount of conductors in that parallel path. Now you have to multiply z per a with respect to the EMF per conductor to get the total EMF generated across the armature terminals. So that's how we arrive at the EMF equation. Is it clear now, Ranjit?
Yes, sir, clear.
Okay, thank you. Let's quickly look at torque generation. It's even simpler when compared to EMF. I will just okay. Now, now let's say I will just quickly draw a diagram here. Same machine. Yeah, and this is the field winding. Now I'm trying to flow IF current through here. My flux will be generated. Same thing. And okay, fine. Okay. So let's say we are trying to rotate my machine with at a speed of n rps per second, and actually the windings is not like that. Let's say these are the poles. My field winding will be bounded across the poles, right? Like this. So this particular field winding, what you see is appears like this, and let's say it is north, it is south, and now here you will pass IF, and it will come like this, and it will traverse like this. Now the current will flow, and this is the direction, and this will be the direction. The field will come out of the North Pole and the lines will enter into the South Pole. That's the convention. Now, this is the flux generated per pole. Phi F is the field flux that is generated. Now, we will have to apply right hand rule here to define the direction of polarity of the induced voltage. So that we already did in the this while we are doing it for the EMF generator, right? So if it is cross polarity for north, it is dot polarity for south. Okay, we'll just okay. Now let's say I have connected my machine to a load. Okay, now this is my machine. This is the terminal voltage that is we have calculated at no load. Let's say this is a switch. If the switch is open, it means that there is no load connected. We have calculated the EMF generated in such no load case. That is S is open. Now we know that the voltage at this case is open circuit, right? V is equals to V open circuit. How much we got? Pz by A phi n volts. How much current will flow in this case through the armature? Zero, because it's open circuit. It's open circuit, right? No current will flow. Now I will close my switch. As soon as I close my switch, a current IA will be drawn by the load because there is a closed part. My motor is rotating. My current is flowing inside the armature winding terminals. My resistor will obviously take some current. That is a load current. Now, when I close the switch, current will start to flow. This is under the condition of S open. Okay. Now, as soon as I close my switch, my IA will pass. Now, at this condition, we want to calculate how much torque my prime mover has to apply, because you see, I'm trying to rotate my machine with prime mover such that it can supply the load. Now, this is my mechanical torque. Like whatever I'm trying to rotate my machine is a mechanical torque. Now, how much torque my prime mover has to apply to rotate my machine in this clockwise direction? So, as soon as I close the switch, my current will appear across the conductors and they will experience some kind of force. So, now to calculate the force direction, because force, if you get the force, it's easy to calculate the torque. Yes, right. Force into radius of the machine will give you the torque. Now that's simple. So to torque, first let's calculate the force. Okay. Now how can we calculate the force here? Now to know the force direction, we need to use left hand rule to find the direction of force. Now let's say everybody take your left hand. Now this ultimately my thumb will give the direction of force. So what will these two fingers do? My index finger is the field direction, and now my middle finger is the current direction. Now if I know the field and now if I know the current, I can calculate the direction of force. See, let's take a conductor under the influence of North Pole. It is a cross convention. Cross convention means my current is flowing into the paper. This is the direction. Now my middle finger is current, right? Now left hand rule. My middle finger is pointing into the field, and okay. Now where is the field? Field is from here. You can see the field. North is from left to right. This is field, and this is field direction. Now this is field, and this is current, and you can see the force, right? It is towards the bottom. It means that you are having this kind of motion. My electromagnetic torque generated will be downwards. Now this is my current into the paper, and this is my field direction. And from the left hand rule, this is middle finger, and this is index finger, and this is my thumb will be downwards. So this will be the direction of my force. My what I can say This is the direction of motion. Here my motion is electromagnetic torque. Sorry. Now we know the direction of electromagnetic torque. Now let's say we have a four-pole machine. Now my machine is running at some n rps per second, and you know the influence of north pole will have cross convention, and the conductor center of the south pole will have dot convention. Now here also we will follow the same. You take any one single conductor and you calculate what is the force the single conductor is being experiencing. Now, the force experienced by the single conductor, we know the formula. It is BIL sine BIL. There will be not there here. So F is equals to PIL. Here again, the B will be the average value of B flux density. The current is whatever current through the parallel path it is flowing, and L will be the length of the conductor. Now, we will again the same condition here. The B will be B average, because as the conductor moves, it will experience different values of B under the curve. Under the north pole and the south pole, that value of B will be varying. Here also we will take the average value of B, and we will proceed with the force calculation. Now see, force for each conductor is equals to B average into the current. Now, if you see, if IA is the total armature current, okay, I have four parallel paths. Now, my current will be divided across the parallel paths. Now, total IA won't flow through the conductor. How much amount will flow to the conductor? It will depend on the number of parallel paths, because my current will be divided. If there are four parallel paths, my current will be divided by IA by 4, IA by 4, IA by 4, and IA by 4. My conductor will see only IA by 4 current. It won't see total IA current. So you have to keep that in mind. The current will be IA by A here, because A is number of parallel paths multiplied by length of the conductor. So that is the force experienced by each conductor. Now I will just substitute. What is the B average we got in the last case? Okay, let's substitute that later. Now we know the torque. Torque is nothing but force into radius of the machine. Now B average multiplied by IA by A multiplied by L multiplied by, how much is the radius? We know the diameter. The radius is nothing but D by 2, right? So you just substitute all the values here. Okay, let me just create another sheet.